Yeah, hi. We are probably all used to using code coverage metrics in our development work. We're used to writing tests in a way that makes our CI pipelines happy. However, I rarely see people talk about why we are actually doing this, where these fundamental testing methods are coming from, and what the limitations are. So that's why today I'd like to talk a bit about the limits of black box and white box testing. Before we get into it, let me quickly talk a bit about myself. My name is Leah Buchberger. I'm a senior consultant for software development at Synwert in Hamburg. Synwert is a multinational consultancy group focused on AI, data science, software engineering, infrastructure engineering, stuff like that. Now, before I talk about black box and white box testing, I'd like to very quickly talk about the testing principles because they kind of serve as the motivation on why we need these methods in the first place. These are the 7 testing principles as defined by ISDQB. And for the most part, today we don't care about these. There's only one of them we care about, namely the second one. Exhaustive testing is impossible. This means that it's, ignoring a few trivial cases, it's not possible to test the complete input space of any arbitrary program. And this raises an interesting question, namely, if we cannot test exhaustively anyway, where do we stop testing? So this is the question that white box and black box testing are trying to answer. Right, so first of all, let's talk about white box testing. White box testing, I actually think it's not a good name for this. A better name is what the ISO standard uses. The ISO standard calls this structure-based testing. The fundamental idea is as follows. In order to detect defects in our code, we actually need to execute the defective code. And therefore, we derive our test cases purely from the source code. Structure-based testing. We derive the test cases from the structure of the program. And of course, we need to determine how well our tests are, and the measure of quality we use for our test suite is called code coverage. There's more, but there's 2 fundamental coverage methods that I want to show you. The first is called control flow-based coverage, and the second is data flow-based coverage. Control flow-based coverage is probably what most of us developers are used to. The coverage items we are talking about is lines or statements, branches or decisions, and conditions and predicates, and of course there are even more. For lines and statement coverage, we care about the individual statements in our source code. So in this case, this is all of the statements that I highlighted with the orange bars on the side. For branch decision, this is a bit more interesting because we not only need to consider branches that actually contain code, but we also need to consider branches that don't contain code. So in this example, I added some comments with the empty else block for our if condition here, and our, in quotes, else block for the for loop. That means that the for loop is completely skipped and is not entered. And the last one is condition coverage, which means we care about the conditions in our program. The coverage item, the thing we measure to determine the coverage, is actually the conditions, the Boolean expressions in our program. There's a few variants on these. The most used one is called multi-condition coverage, where we not only care about the atomic Boolean expressions, but we care about all Boolean expressions. So in this case, this would also mean the big expression on top. The data flow-based coverage metrics are not that popular, I guess. And again, I want to present to you 3 coverage items we can look at. Of course, there are even more that might be interesting, but for today, let's only focus on these 3. The first one are the variable definitions and assignments. These are called defs traditionally in data flow-based coverage, and these are all the definitions that we use in a program. Our input parameters are obviously definitions. This is where values come into our program, in this case the function. Even the static assignment to result is a definition and assignment. the assignments to the exponent here and to the result in the for loop are also assignments. So every assignment in the source code is one thing that we consider a coverage item. Computational uses are when we actually use the variables for computation. So for example, this exponent here inside of this decrement operation can refer to either the parameter exponent or it can refer to the recursively decremented exponent. So this is actually two different computational uses because it refers to two different definitions. A similar, the base one here only refers to the base parameter because there's no other definition for base. However, this result here can refer to two different definitions again, the static result above the for loop or the recursively calculated result inside of the for loop. And this result at the bottom can either refer to the result above the for loop or the result inside of the for loop. I'll show an example later on how this works in practice. The last one is called predicate uses. This is every time we use a variable as a predicate, as a Boolean expression. And in this case, the top ones are quite easy. The exponent up there only can refer to the exponent parameter. The base can only refer to the base parameter. But this exponent here can either refer to the input exponent parameter or to the decremented exponent parameter. I kind of skipped what this program actually does. This is a very naive implementation of a power function. So we have a base and an exponent, and we calculate the exponent power of base. So what are the limitations then? So the first one is that these methods, these white box testing methods, might not be able to detect when features are missing. And they might not detect specific edge cases depending on which methods that we use. Let's look at an example. Again, this is the power function as from earlier, but this time we have to change a few things in order to demonstrate this limitation. So first of all, let's get rid of all the floating points. We are only dealing with integers now. And secondly, because we are in the integer space, a negative exponent doesn't make sense. Negative exponent would mean that the result is a fraction which does not exist in the integer. So these are the two modifications that we add. So we change everything to int, and we add this new illegal argument check for if the exponent is negative or not. Let's select a few coverage metrics. Let's use statement coverage, which is the one that basically any coverage tool can deal with. Let's use definition coverage, branch coverage, and also use the computational use coverage. And let's start with two test cases, one with an exponent of -1 that we expect to panic, and one with an exponent of 1 where we just expect the base as the result. Now let's take a look at statement coverage. In the first test case, we enter the if block at the top and then just panic. So basically 2 out of 6 statements are covered by this first test case. The next test case then skips the if condition and enters the for loop, so it basically covers all the rest of our statements. 6 out of 6 statements are covered. For definition coverage, we have to look at all the definitions we have in our source code, and then we have to determine how many of them or what percentage of them are actually used inside of the program. So the first test case only uses the exponent parameter because of short-circuiting. The second part of the if expression is not evaluated. So we only have 1 out of 5 definitions that are reached by this first test case. However, if we then add the second test case, all of the other definitions are used at some point. Therefore, we have 5 out of 5 definitions used. That's 100%. Let's look at branch coverage. As I said earlier, there's actually 4 branches in here. We have the branch in the if condition where we just panic. We have the virtual else branch in case we skip the if block. We have the for loop, and then we have the virtual else block of the for loop that we enter when the for loop is completely skipped. In the first case, we enter the if block and then just panic. So 1 out of 4 branches is covered. In the second case, we skip the if block. We enter the virtual else branch, and then we enter the for loop, but we never skip the for loop, therefore there's one branch missing. So 3 out of 4 branches are covered. Now, in pure whitebox testing, what we would do now is we would come up with a new test case that now brings our coverage back up. So in this case, let's use one that just has the exponent 0, so it skips the for loop, and then this virtual else branch after the for loop is also covered, 4 out of 4. Let's take a look at C uses. The circles, or the, I guess, ellipses, are all the locations where we use variables as a computation in this case, and the arrows point to their respective definitions. So what we want to have is that all of these arrows are at some point used. In the first test case, none of our arrows are used because we just leave the function with the panic and we never actually execute any computation. The second one enters the for loop once, which means that all of these computations here are executed. However, they're computations that use the recursively computed result and exponent are not used. For these expressions to be used, for these definitions to be used, we would have to repeat the for loop, which is not the case here. And the final return result at the end refers to the computed result inside of the for loop. It does not refer to the initial result. So this is 4 out of 7. This new test case that we added earlier then skips the for loop, so the returned result is actually the initial static result we assign before the for loop. Now we have the same thing again. We only have 5 out of 7 C uses covered, so we come up with a new test case that now brings our coverage back up. The thing we have to do here is we have to repeat the for loop multiple times. So let's just use 3. So in this case, we have power of -3 and 3. And this time, the result inside of the for loop also refers to the result that we compute in the same line. And the exponent in the for loop action actually also refers to the decremented exponent. So now we have 7 out of 7 C users covered. Perfect. 100% coverage in total. Now, can I get a show of hands? Who thinks we've tested enough? Okay, very few. Very good. Another show of hands. Who found the defect? Who found the bug? Turns out there's actually a bug in there. This is not right. The thing we do here is we check if the base and the exponent are both 0, and if that's the case, then it's undefined behavior, or actually it's undefined in math in general, so we just panic. However, in this case, the operator is wrong. It should be equals equals instead of bang equals. And none of our metrics actually were able to discover this bug. I kind of cheated here because I selected the example and I selected the coverage metrics here specifically to show that stuff like this can happen if you only care about coverage. P-use coverage, that is predicate use coverage, would have discovered this because it would force us to actually have a test case that uses this initial exponent as a predicate. That would be this first line. And multi condition coverage would have also found this because it forces us to evaluate all the sub-Boolean expressions. And therefore, we would have also have to have a test case that actually triggers this defect. Right. Then let's see about the second limitation. Of course, there are more limitations, right? But this is the two that I want to talk about. The second one is test coupling. Because whitebox testing only works if the tests directly are created or derived from the source code, we have this weird situation where we cannot really easily change the source code unless we also change the tests. And also have an example. This is the same power function from earlier. Let's use the same metrics and use the same test cases. This implementation of the power function is very slow, right? This is like the naive implementation of a power function. And there's actually better implementations. Let's use one of them. This looks a bit more complicated. This is called Montgomery's ladder. It's a implementation of exponentiation by squaring. It has two big advantages advantages compared to the original version. The first is that this is much faster. This is actually logarithmic runtime instead of linear. And secondly, this one does not leak the exponent value as a timing side channel. So this one you could actually use for like cryptographic stuff, RSA, whatever. But now we have a problem because we still are using the same test cases. We now have this blob, this piece of code in there that's never actually tested. The reason why this is never actually tested is because this if block here is only reached if we have an exponent that's larger than 0 and where the binary representation contains a 0. But the only two test cases that we have with an exponent larger than 0 are 1 and 3, and both 1 and 3 in binary only contain 1s. So this block, this if block, is actually never reached, and therefore our coverage is way lower than before. In fact, if we average everything, then we have about 76% coverage. And this is what I mean with test coupling. We have to change the tests when we change the implementation. And this is true in this direction. If we change the implementation to be more complicated, then the code coverage drops because we have to have new tests that now test the specific increased complexity. However, we have the same problem if we reduce the complexity, because then we have tests in our test suite that never actually test anything specific, because the tests are derived from the source code, right? Right. Let's take a quick look about black box testing, what limitations black box testing has. Black box testing is also called specification-based testing. Again, this is the term that the ISO standard and also the IEEE and the IEC standard use, and I think it's a better name anyway. The essential idea here is that we only care about the behavior that's specified. We care about the expected behavior of the program. And therefore, the idea is that we derive our test cases from the specification. And the measure of the quality of our test cases is usually called test, or I think a better term is requirement coverage. There's again loads of different variation on how to do this. I would like to focus on two. The first is called equivalence class partitioning, and the second is boundary value analysis. Equivalence class partitioning is kind of simple. We look at our specification and then we try to group inputs that behave similarly. Here's a small toy example. Let's say we have a function that recognizes the weekend based on the number of the day of the week. So our specification looks something like this. Our input is an integer, where 0 is Monday, 1 is Tuesday, and 6 is Sunday, and stuff like that. And our output is a Boolean, where true means it's weekend and false means it's a normal weekday. And anything that's outside of the week range is considered invalid. Now let's take a look at the number line on the right. The weekend is the range from 5 to 6, and the weekdays are from 0 to 4, and everything that's below -1 and above 7 we consider invalid. And what equivalence class partitioning does is that because we assume that all of these classes behave similarly, we only actually need one test case for each class. It could look something like this. So we have one test case for each class, and this is the test suite that we are working with. Let's maybe take a look at a bit more complicated example. Let's go back to this power function we had earlier. Let's assume we are in the integer space, so our inputs are a the base of the power function as an integer, and the exponent of the power function as an integer. And we expect the output being 1. If the exponent is 0, 0. If the base is 0, we expect the normal power function stuff, but always positive if the base is greater than 0. And we expect the normal power function stuff but with alternating signs if the base is less than 0. And the we consider a negative exponent as invalid because, again, we are in the integer space. It means that a negative exponent would mean a fraction. And if base and exponent are both 0, then we consider this invalid because it's not defined in the normal power function. Right, so first of all, exponent 0 would look something like this in our 2D graph here. Again, notice how the middle is left out because the middle is a special case. It's an error case. If the base is 0, of course, then the output is 0. If base is positive, then we have the normal power function behavior, but always positive. And if base is negative, then we have the normal power function behavior, but with alternating signs. If the exponent is negative, then this is invalid. And at the origin, with base 0 and exponent 0, this is, of course, also invalid. And now again, with equivalence class partitioning, we just would create one test case per class. And then we have a test suite that looks something like this, for example. And this, we assume that this would then just test all of the different behaviors that can occur in our program. In fact, the issue we had before with whitebox testing, where the case with base and exponent being 0 was not handled correctly, this test suite would actually have caught this. Right, let's take a look at boundary value analysis. The idea of boundary value analysis is that we start with our equivalence partitions, but then we select test cases at the boundaries between our partitions. So maybe just give you an idea on why this is useful. Let's assume we have the same test suite for this weekend function we had before, and let's assume our source code looks something like this. So the first line with if they less than 0 or they greater than 6, this is fine, that's correct. But then we have return day greater than 5. This means that only Sunday is considered weekend, and we cannot have that. So what boundary value analysis does is we take a look at all of our different equivalence classes that we have, and then we look at the boundaries between these classes. So for example, in the first invalid case, that's the left invalid class, that's 0 or below, or actually just below 0. We have an inner boundary, that's the first case that's invalid at -1, that's the inner boundary. And we have an outer boundary, that's the first case that's not invalid, in this case 0. A similar thing happens for the upper invalid class, where 7 is the inner boundary because it's the first value that's invalid, and 6 is the outer boundary because it's the first value that's not invalid. For the weekdays, we actually have two boundaries: one boundary to the invalid class and one boundary to the weekend class, with 0 and 4 being the inner values because these are the first values that are inside of this class, and -1 and 6 being the outer boundaries because, -1 and 5 being the outer boundaries because these are the first values that are not actually considered weekdays. For weekends, it's essentially the same. We have two boundaries, one boundary to the weekdays, one boundary to the invalid class, and the inner boundary values are 5 and 6, and the outer boundary values are 4 and 7. Now, this is way better. This would have caught the bug from earlier. Sorry. However, this could still cause problems. Let's assume our source code looks something like this. In this case, the return day greater or equal to 5 line is fine. However, the condition is wrong. This condition only checks if the day is -1 or the day is 7, which means the boundaries are checked by the source code, and the boundary value analysis would say, yes, this is fine, this is correct. However, this is not correct, right? Because if we, for example, put in -2, this would fail. The test suite would say this is okay, but it's actually wrong. This is not correct. Yeah. And boundary value analysis actually has a solution for this. It's called three-value boundary analysis. In this case, we not only care about the first value that's inside of our class, but we care about the second value as well. So for the lower invalid class, this would be -2, because -2 is the second value that's inside of the invalid class on the bottom. On the top, this would be 8, because 8 is the first value inside of the invalid class on the top. For the weekdays, the 2, 3 value boundaries would be 1 and 3, because those are exactly one step removed from the boundary, from the actual boundary values. And for the weekend, this would be 6 and 5. However, since 6 and 5 are also the inner boundary values, since the class is only 2 values, this does not do anything. The resulting test suite then looks something like this. So this is 10 test cases that test all the boundaries, the 2-value boundaries as well as the 3-value boundaries. Now let's talk about the disadvantages of black box testing, the limits of the black box testing. Now the first one is probably all obvious, right? It's called specification-based testing. We need a specification. We cannot use black box testing without a specification. However, it does not really matter how the specification looks like. It could be a formal specification. It could be acceptance criteria of a ticket. It could be, I don't know, an interface definition. It could be a design contract. It can be whatever. But we need to have some sort of specification that tells us how the program should behave and that we can use to derive our test cases from. This is a major disadvantage because often we don't have this. And the second one is that we cannot detect bugs, we cannot detect behavior that is implemented but not specified. Or to be more precise, we can detect it, but it's up to chance whether or not we detect it. Let me give you an example. Let's go back again to this 3-value boundary value analysis test suite from earlier. It's 10 test cases. It's already quite extensive for such a primitive function, right? And still, if the function looks something like this, we cannot detect this. In this case, there is this day equals to 2 check on the bottom. This essentially declares Wednesday as weekend. And I'm not opposed to having off on Wednesday, right? But this does not fit the specification. This is a bug. And black box testing was not able to detect this because it's completely outside of the specification. Depending on which white box testing method we used, for example, p-use coverage would have caught this, right? Right. Now let's go to the conclusion section. With all this stuff, there's one big problem, right? Neither black box testing nor white box testing are actually perfect. Both of them have specific cases that they just cannot deal with. In the case of white box testing, it cannot deal with behavior that's specified but not implemented. That's something that white box testing just cannot deal with. And black box testing might miss stuff that's implemented but not specified. So like the assuming Wednesday is weekend in the previous example. That's something that black box testing only can detect by chance and not by design. So here's my recommendation. I would recommend use black box testing if possible. Where applicable, use black box testing because it uses the specification. It assumes the expected behavior as the basis for our tests. However, I would still use code coverage metrics, like for example line coverage, branch coverage, whatever, as a sort of sanity check, in the sense that if I use black box testing to derive my test cases, and I have 100% equivalence class coverage, whatever, or I have 100% 2-value boundary analysis coverage, and I still only get maybe 10% line coverage, then something's wrong, right? Then either the implementation does stuff that's not specified, or the implementation is much more complicated then it should be, or yeah, probably should be. Or what could also happen is that the specification was missing something. Maybe there is a specific case that's actually important, but the specification missed. In any case, low code coverage with high specification coverage could indicate that there's something wrong, or there's something that needs to be looked at here. So that's my recommendation on how to deal with this. Right. This talk is roughly based on a blog post I wrote some time ago. The blog post actually goes into a bit more detail, specifically when it comes to black box testing, because there's also some fancy stuff you can do, like combining equivalence classes and using the fact that they might overlap and stuff like that. The blog post goes into a bit more detail here. The left one is my personal blog, and the right one is Medium, in case you prefer that. And with that out of the way, I'd say let's go to the Q&A section.